Hello everyone, this is Honors College Algebra, Chapter P, Section 1 notes. I'm just going to do the first page front and back for today, and then tomorrow I'll make another video and we'll finish up that with absolute value. Okay, so in this part, which you may have seen in Honors Algebra 2, that we take the real number line, you know, this number line, from negative infinity to positive infinity, and 0 between, because remember 0 is not positive nor negative. And we take this number line and we break it down into smaller subsets. The first set, which is the smallest set of real numbers, is the natural numbers. And in many textbooks, you'll see the natural numbers be represented as a capital N with a double bar. Okay, and this is what we call the counting numbers, because you naturally start counting with the number 1. So these are our counting numbers. We're going to illustrate with set notation, which is these curly braces. Draw them the best that you can. And we'll show that number 1 is in the set of counting numbers, number 2, number 3, and it keeps going in that fashion. And in our examples column, we'll just put a couple of our favorite numbers, like 4, 7, 10. Okay, we're not going to list them all because there's infinitely many. Whole numbers. The symbol for whole numbers is a capital W with double bar along these diagonals. Okay, so if you see that in a textbook, know that they are talking about the set of whole numbers. Well, what do we add to the set of counting numbers on the number line to call them the set of whole numbers? Well, you know, to me, I look at this O in the middle and it reminds me of a 0. And that's exactly what we add to the set of whole numbers and call them we add that to the set of whole numbers from the counting numbers. So you add 0 to the counting numbers. So when you put 0 in that set, then we call that the whole numbers. And so this little subset grows by one element. 0, 1, 2, 3, keeps going. And a couple of examples are 0, 5, 12. All right, the integers. Now you might think the letter I is the symbol for integers, but it's not. It actually is a capital Z. I'm not quite sure why, but the double bar Z is the integers. And what do we add to the subset of numbers, you know, from this real number line to call them the integers? Well, some of you have got it. Yes, negative numbers. So add negatives to the whole numbers. Add negatives to the whole numbers. And you get the set of integers. So we'll show that with a larger set when it's starting out with an ellipses. Because we're not going to write all the negatives. We'll just start at negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. A couple of our favorite negative numbers, negative 32. Of course, we want 0 in there because it is an integer, and I chose the number 50. Rational numbers. You would think R is the symbol for rational numbers, but it's not the symbol for rational numbers because the double bar R is the symbol for real numbers, all of the numbers on the number line. This is called the real number line. All numbers on it are real. If you think about and break this word down, you see the word ratio in the word rational. And a ratio is a fraction, could be written as a fraction. And the result or the answer you get when you divide two numbers is called a quotient. And so the symbol for rational numbers is a Q with the bars on the side. It's capital Q. So this is a little bit wordy, so don't write too ginormous. This is the set of numbers of the form A divided by B, where A and B are integers And b is not allowed to equal what? Anyone know? We'll take a look at where b is in this fraction. It's in the denominator, so b can't be 0. Remember, division by 0 is undefined. Here, if you were to convert your fractions into decimals, these decimals would either terminate or they would repeat. So we say here terminating or repeating decimals. So like, negative 17. Set of numbers of the form a and b, where a and b are integers. Well, I could rewrite this as negative 17 divided by 1. Both negative 17 and positive 1 are integers. And so, yeah, that's a rational number. I can put any integer over 1 and have it be a rational number. 1/2 is a rational number. Why? Because 1 and 2 are integers. And when I get the decimal equivalent for 1/2, that's 0.5. And notice no digits other than 0 will follow it. And then, of course, another example here would be like negative 2/3. The decimal equivalent to that is negative 0.66 repeating. And so that's going to satisfy our conditions for terminating or repeating decimals for our rational numbers, which is different from our irrational numbers, because the irrational numbers is a set of numbers whose decimals are neither terminating nor repeating. Excuse me. So they don't stop and they don't repeat. Like pi. Pi is the most famous irrational number. And you know the characteristics of pi. Decimals don't stop and they don't repeat. And in fact, you cannot express these irrational numbers as a ratio of two integers. So cannot be expressed as a ratio or as a quotient. I'm writing too large, of two integers. Okay, so like pi. Pi is approximately equal to 3.1415926 and a bunch more. The square root of 2 is irrational. It's approximately equal to 1.414214 and a bunch of decimals after it. And then, of course, negative, or the opposite of the square root of 3, is approximately equal to negative 1.73205 and a bunch after. So take a look at those, and we're actually going to categorize these values here into the sets of natural, whole, integer, and rationals after we make this Venn diagram. Now this whole box, this whole big giant box right here, is the double bar R. See that double bar R? This means real numbers. So all the numbers in this box, this whole big giant rectangle, is they're all real numbers. They can be found somewhere on the real number line. Our largest set, if you've noticed, is our rational numbers. So we put the rationals outside here. See, the rationals are inside the box of real numbers, but rationals and irrationals are separated because these have decimals that either stop or repeat, and these have decimals that don't stop and don't repeat. But it's still in the umbrella of real numbers because those numbers can be found on the real number line. Okay, the very smallest set, well, we saw up here, the smallest set was our counting numbers 1, 2, 3. And so these are our natural numbers. And when we add 0 to the set, we get the whole numbers. Now, notice, Every natural number is a whole number, but not every whole number is a natural number. So the only difference between these two sets here is the number 0. And then what was in between? Those integers. Okay, so you add negatives. So we have to separate, like every natural number can be classified as an integer, and every whole number is an integer. The only difference between these two sets, again, one more time, I sound like a broken record, is the number 0. And all of these numbers are rational numbers because I could take any of these and put them over 1 and have a set of rational numbers. Now we're going to look down here. Remember, sometimes some numbers are incognito. They take on a different form. They're like in costume. Okay, and so negative square root of 9. Well, root 9 is really 3. It's 3 in disguise. And so, you know, this number is equivalent to negative 3. Let's look at root 7. That's an irrational number. You could type that in on your calculator and see. 3.47 repeating, that would be 3.47. 2 pi. Well, pi is irrational, and 2 times pi is still going to be irrational. So that's going to come down here. The fourth root of 7. Try as you may to find some number multiplied by itself 4 times to equal 7. I don't think it's going to happen. This guy here is irrational as well. And again, you can put it on your calculator. And then we look at this decimal right here. Well, do we have any repeats? The ellipses is telling me that it keeps going. So I'm thinking this is irrational as well. Well, let's categorize. We want the set of natural numbers. Now remember, a natural number is a counting number. Do we count with negatives? No. Do we count with zeros? No. Do we count with parts? No. Root 7, irrational. 3.47, repeating. No. Because that's going to be in our rationals. Okay, with decimals that repeat. 2 pi, irrational. Oh, cube root of 125. What is the cube root of 125? What number times itself 3 times is 125? That would be the number 5. This thing is equivalent to the number 5. And 5 is a counting number. I'm going to put it in my set, though, as what's in that. This is the cube root of 125. And that's irrational, and that's irrational. So I think I'm done there with my naturals. Now remember, if it's a natural number, it's also a whole number. So I'm going to start out this set. Follow your diagram. Natural numbers is inside the set of whole numbers. So if it's a natural number, it's a whole number. I'm going to start out with that. And what else do I add to the set? Well, 0. 0 is going in that set. All right, integers. Integers are our negatives. Negative 5. This is equivalent to negative 3. Integer, integer, not integer. Integer, not integer. No, no, no. Yes. No, no. So what's going to go in there? Everything that's in that set. Cube root of 125. 0 for sure, negative 5, and the opposite of the square root of 9, which is negative 3 incognito. Okay, what's next? Well, we've got the rational numbers. Remember, if it's natural, whole, and integer, it classifies as a rational number as well. So I've got cube root of 125, 0, negative 5, opposite of the square root of 9. Are there any other values that fall into? We knew that this one here, 2 pi, was irrational. We saw that the fourth root of 7 was irrational, and so was that one. Was there any other ones? Oh, yes. The square root of 7 was irrational. So negative 5 we have in the set. Negative 9. Oh, negative 4/3 and positive 2/3. I'm going to put that into the set. Negative 4/3 and positive 2/3. And is there anything else? One more. 3.47 repeating. And we close the set. And now here we're just going to put our values of the irrational numbers in. Square root of 7, fourth root of 7, 2 pi, and 4.38739635 ... So if you have questions on classifying these into their subsets, leave a post on the discussion or ask about it in class. I apologize for this thing being moved around on the screen while I'm making this video. Okay, side 2 of the notes. We have here a chart, and it's going to give us the name of a set, the description of what is in the set. We're going to give set builder notation and then interval notation, and then we're going to give a graph right here. So the name of the set is set C, and what's in the set are elements of X that are less than 1. So set builder notation, we're going to write, this is set notation right here. And so I'll illustrate up here. This is set notation. So it's a set of all X. This bar means such that. Okay, I'm using X because X is the variable that I'm using. It's a set of all X such that X is exactly what this says, less than 1. The interval notation. Well, the interval notation is going to look like, well, where am I going? I'm shading to the left to negative infinity. You know, if I think of my number line is going from negative infinity to positive infinity with 0 in the middle. If I'm shading left, I'm shading in the direction of negative infinity. And how you want to set up your interval notation is like from left to right on the number line. I'd be coming in from negative infinity first up to the number 1. Now, I'm not including the 1 because it doesn't say equal to right here. So we have to use parentheses, okay? So again, the parentheses means does not include the value in the set, okay? So I'm using parentheses to say it doesn't include. We can never bracket infinity, by the way. Okay, infinity is not a number, so we're not including infinity in the set. We're just saying that these numbers don't stop. And then when you use brackets, it means included or it belongs to the set. Okay, and we'll see that here when we have some equal to situation. So this just means set of all X such that X is less than 1. That's what this says. My interval notation. Well, if I think of this in terms of a number line, I'd be starting at 1 and shading to the left, but not including it because it's not equal to it. And so that's why I have to use the parentheses. And then we're actually going to give the graph. So here's my 1. And then you must give this thick arrow. Don't just shade up to this arrow because this arrow belongs to the number line. This arrow belongs to the shading. Okay, so I need to see a distinct arrow on your number lines when you graph these. All right, set D. X is greater than or equal to 4. Or equal means include. So I've got the set of all X such that X is greater than or equal to 4. This time, if I'm thinking about this on the number line, I'd be at the number 4, and I'd be shading to the right because greater than is to the right. There's my thick arrow. And now the question is, do we need a bracket or parentheses? Well, if it's equal to, I need a bracket. So I'm going to bracket to the right. And my interval notation is going to look just like this. This arrow is going to positive infinity. Remember, this one was coming in off of negative infinity on the number line. So I'm going to bracket 4, and go to positive infinity. And remember, we can never bracket infinity. X lies between two numbers. Okay. So I've got X such that I'm between two numbers, -5 and 2. -5 is smaller than 2, so I'm going to put -5 here. I'm going to leave a space because I need some inequality symbols. I'm going to put the x, and then I'm going to put the positive 2, and I'm going to close my set. So x is between negative 5 and 2. I have to read the rest, including negative 5. Folks, if negative 5 is less than negative 2, then the inequality arrow has to point left. It has to. If I read this backwards, it's going to say x is greater than negative 5, or negative 5 is less than x. But including means equal to. And excluding 2, again, as long as the smaller number is on the left side and the bigger number is on the right side, the arrows always point left because the smaller number is always less than a bigger number. Okay, including negative 5 and not including this. So what does my graph look like? Well, I need a bracket on negative 5. And I need a parenthesis on positive 2. And I'm going to shade between. And what does my interval notation look like? Well, it looks exactly like this. Negative 5, comma, 2. Bracket on negative 5, parenthesis on positive 2. You try the next one. Pause the video, and then bring the video back on. Okay, so set B says x is not positive, not positive. What number in the number line is not positive? 0. 0 is not positive, so that's my boundary. The boundary is 0. Okay, so I know it's not positive. If I include the 0, is 0 not positive? Yeah, 0 is not positive, so 0 is included. And it's at least negative 7, so I really am in between negative 7 and 0. Remember, negative 7 is less than 0. So in your interval, or your set builder notation, rather, you've got x such that x is between 0 and negative 7. Folks, keep in mind and be cognizant of the fact that negative 7 is less than 0. So it has to be to the left of it. Remember, our inequality arrows always point left. X is in the middle. And now is not positive. 0 is not positive, so I'm including the 0. And is at least negative 7. Well, at least means it can be negative 7. So I've got a bracket thing going on here. I'm in between negative 7 and 0, including the negative 7 and including the 0, and my graph is going to look the same way, and I shade between. So again, if you have questions, post it on the discussion, or ask a question in class when I see you in class. That's how we're going to convert from set builder notation to interval notation. We're going to talk about union and intersection of sets really quickly. This isn't that too difficult to figure out. A in union with B, this means in union. And union means to unite, to bring together. This is A in union with B. It's a set of all elements that are in both set A and set B at the same time, and nothing else. So the union of these two sets, to bring together, it's everything in set A and everything in set B together at the same time, uniting them, which is different from an intersection. An intersection is the overlap. This thing here means intersection. You know, and if you think of an intersection like an intersection of two roadways, okay, this street and that street, this part here is the intersection. It's the part that they have in common or the part that overlaps. And so when I'm looking at A in union with B here, it's this piece here where they overlap, only the overlap. Now these examples here are going to come from the names of these sets here at the above the top of the page. And I can't really fit everything on this video screen, or you won't be able to see it so well. And so I'm just going to refer to the sets above. A and B, sets A and B are the bottom two sets. And A goes from -5 to 2, and B goes from -7 to 0. So if I'm uniting these sets, you want to be farthest left and farthest right. Sometimes the two sets have elements in common, and sometimes they don't. Sets A and B do have elements in common. They have from -5 to 0 in common. If you look here, they have from -5, because -5 is in here somewhere. And 0, this one stops at 0, but this one goes to 2, so 0 is in here. So they have from -5 to 0 in common. But farthest left to farthest right for the union of the two sets would be -7 to 2. -7 with a bracket and a 2 with a parenthesis, and that brings the two sets together. So I'd like you to try these. Pause the video and try these and see if you can come up with the same answers that I get. Okay, hopefully you did pause the videos, and we'll look here at the intersection of A and B. Remember, intersection is what they overlap, what they have in common. And I pretty much talked about that just a few minutes ago, the fact that they have from -5 to 0 in common. And notice there's a bracket on -5 and a bracket on 0. So that's my bracket, -5 to 0 with a bracket. The union of sets C and D. C and D are the top sets. So I'm going from, let's take a look at this, -infinity to 1, and then 4 to +infinity. These two sets don't share anything in common, but I could still write the union of the two sets. I just have to write it like this. From -infinity to 1, remember there was a parenthesis, so we have to keep that, in union with 4 to infinity. And that's how you write the union of two sets that have no elements in common. And of course, since we saw that sets C and D have nothing in common, you would write the empty set like this. It's the set with nothing in it. It's empty. Or write the circle with a line through it. This also means empty set. Please don't ever put the empty set inside the empty set, because then this set would no longer be empty. It's either one of these, not both. Union with sets A and C. Well, A is -5 to 2. Set C is -infinity to 1. When I bring both of these sets together, I definitely have to start at -infinity. And the farthest right, well, look, set C stops at 1, but set A stops at 2. So I'm going to put the 2 in there, and the 2 had the parentheses. And then if I'm looking for what elements A and C those two sets have in common, that's just the intersection of sets A and C. What do those have in common? Well, they have from -5 to +1 in common. So I go -5 to +1. There is a bracket on the -5 in set A and a parenthesis on the 1 in set C. Okay, so tomorrow's lesson we are going to pick up with the second part of P1. And you'll have an assignment. Just follow everything on Schoology. If you have any questions, please let me know, and we'll take care of the questions there. All right, have a great day.